Today, we're exploring the evolution of artificial intelligence, from the foundational convolutional neural networks, or CNNs, to the groundbreaking advancements like GPT models. Understanding these underlying architectures is crucial. It distinguishes true algorithm engineers from those who merely use pre-built packages. While technologies evolve, these foundational concepts remain timeless, providing a deeper insight into AI's capabilities and ensuring we're equipped for future innovations. Welcome to the Interview Dividing Line. Here, we explore two types of tech professionals. First, the package warrior, skilled at using APIs, running demos, and following tutorials, yet stumped by questions like, how does the attention mechanism work? Then, the algorithm engineer, who grasps the reasoning behind architectures, the issues they solve, and how to adapt as tools evolve. Remember, while tools and APIs change constantly, the core logic remains the same. Welcome to our journey through AI evolution. We start with convolutional neural networks, where AI learns to see by transforming pixel grids into recognitions like cat or dog. Next, recurrent neural networks bring memory to AI, enabling sequence reading, but with limitations. Then, transformers revolutionize the field with the powerful notion that attention is all you need, paving the way for modern language models. Finally, we explore Bert and GPT. One excels in understanding, the other in generating. Welcome to the first part of our presentation on convolutional neural networks, or CNNs. Have you ever wondered how artificial intelligence can look at an image and identify a cat? This fascinating process unveils a fundamental truth about machine perception. In Chapter 1, we'll explore how CNNs mimic the human brain's ability to recognize patterns, allowing AI to interpret images in ways that are transforming technology today. Today, we're exploring a critical difference between images and language. With images, features like pointy ears and whiskers define a cat, regardless of its position. But in language, order is crucial. The phrase, "I eat apples," means something entirely different from "apples eat me." This distinction, features versus order, explains why AI technologies could recognize images long before they could effectively understand and generate human language. Let's explore how convolutional neural networks, or CNNs, work by first scanning and then compressing images. Convolution acts as a feature hunter, using small windows to search for specific patterns like eyes or a mouth. Pooling follows by keeping only the strongest signals, similar to highlighting key points in notes. This powerful combination led AlexNet in 2012 to achieve a groundbreaking 15.3% error rate in image recognition, surpassing even human accuracy. Let's talk about a major limitation of using convolutional neural networks, or CNNs for text. CNNs interpret language as a simple bag of words, meaning they don't recognize the order of words. For example, "I eat apples" and "apples eat me" are seen as identical, ignoring their distinct meanings. This makes a CNN-based language model like a parrot that repeats words without understanding their context or coherence. Welcome to Part 2, RNNs, where AI starts to remember. Unlike CNNs that are order-blind, recurrent neural networks, or RNNs, address this by looping back to previous information, allowing them to remember context. Think of it as a memory notebook. For example, it recalls "I" when reading "eat" to determine who's eating. Then, with apples, it connects the dots. The object being eaten is apples. RNNs bring context into AI processing. Today, we'll explore the two major flaws of recurrent neural networks. First, RNNs can't parallelize. Imagine a single window queue where each word waits for the previous one, making training on large datasets unbearably slow. Second, they suffer from forgetfulness. As information travels through the network, it fades, causing long sentences to become incoherent. These limitations stall AI's text comprehension, highlighting the need for a revolutionary solution. In 2017, Google introduced a groundbreaking paper titled "Attention is All You Need," marking a pivotal moment in AI history. This paper made a bold claim: eliminate convolutions and recurrence, and focus solely on the attention mechanism. This idea gave birth to the transformer model, which has since become the foundation for modern large models, including GPT and ChatGPT. Welcome to Chapter 3, the era of the transformer. Let's explore the attention mechanism. It works similarly to how we read. When we encounter the sentence, "I love China, how about you?" our brain doesn't process each word individually. Instead, it quickly identifies key connections. I is strongly linked with love, and love connects strongly to China. However, love and you to focus are less related. Machines use this strategy to focus on relevant words, enhancing understanding and efficiency. In the realm of parallel computing, let's contrast two approaches: RNNs and transformers. Think of RNNs like a single service window, processing items one by one, which can be excruciatingly slow, especially with large datasets. Now, picture transformers as an array of open windows, tackling everything simultaneously. This parallel processing capability dramatically speeds up computations, revolutionizing our ability to train large models effectively and efficiently. Now, let's address the question of order in transformers. If all words enter the model simultaneously, wouldn't the sequence get jumbled? The designers had a brilliant fix: position encoding. Each word is given a seat number, like a ticket, ensuring the order remains intact. By merging the word's meaning with its position, we maintain both order and parallel processing. This combination of attention, speed, and order creates a true language master. Welcome to Chapter 4, where we delve into the differences between Bert and GPT. Bert, known as the Understanding Master, utilizes the Transformers encoder to read text bidirectionally, enhancing its ability to comprehend meaning. In contrast, GPT, the Generation Master, employs the Transformers decoder, processing text only from left to right. This design enables GPT to excel in creating and generating fluent, coherent text. Let's explore these fascinating models further. Our next topic is BERT, which stands for Bidirectional Encoder Representations from Transformers. BERT has a unique ability to understand context by looking at both the words before and after a blank. For example, in the sentence, "He eats lunch," BERT considers the entire sentence to find the right word. This powerful understanding also enhances plagiarism detection, identifying subtle rewrites like changing economic development to economic takeoff as still plagiarized, because the meaning remains unchanged. Welcome to our discussion on GPT, which stands for Generative Pre-trained Transformer. GPT writes text using unidirectional generation, meaning it moves forward without knowing the ending. It uses a technique called unidirectional attention, where future words are masked. For example, it sees "where am I?" then guesses the next word like "going" and so on. This approach mimics human language patterns, making GPT's output sound remarkably natural and fluent. Welcome to the learning formula of GPT, combining pre-training and fine-tuning. First, we have fine-tuning, where GPT becomes an expert by training on specialized documents like legal texts, code, or medical literature. Next is pre-training, which involves feeding GPT a vast amount of information from books, web pages, and academic papers, equivalent to 9 years of education plus university. Together, these steps create a highly knowledgeable and adaptable AI. Welcome to the fascinating world of GPT's brute force miracle. When GPT-3 reached its staggering 175 billion parameters, something remarkable occurred: emergence. It was as if logic suddenly clicked into place. This massive model began producing poetry, debugging code, and reasoning logically, all without being explicitly programmed to do so. These incredible capabilities emerged purely from scaling up the model, showcasing the unexpected power of sheer size in artificial intelligence. Let's explore the full evolutionary arc of AI models. CNNs revolutionized image analysis by learning to identify features, regardless of position. RNNs advanced sequence processing by remembering order, letting context flow through text. Then came transformers, which scaled focus using attention mechanisms, parallel processing, and position encoding. Finally, Bert and GPT emerged, mastering deep comprehension and fluent generation. Together, these innovations form the backbone of modern AI. Welcome to the coolest tech romance of our time. Every request you make to AI, like planning a trip or writing a report, stems from years of engineering breakthroughs. Mastering the foundation of these technologies is key, because while tools evolve, architectures remain. By thinking in principles, you can align models with the problems they solve. We're still at the beginning, and those who grasp these fundamentals will shape the future. Keep exploring.